Hey everyone, and welcome. Today we're going to demystify one of the weirdest glitches that can happen inside our computers, something called a deadlock. We're going to talk about what it is, why it's so tricky, and what it actually looks like when computer programs get stuck in a permanent, digital standoff. But first, have you ever been just completely, totally stuck? You know that feeling where you can't move forward because you need something from someone who, it turns out, needs something from you? It's a super frustrating loop, right? Well, believe it or not, that exact feeling is the perfect way to understand a huge problem in computing. So, picture this. You've got a narrow country road, only enough room for one car to pass. One car's driving along, everything's fine, and then bam! Another car appears, coming straight towards it from the other direction. They end up nose to nose. Now for either car to get by, one of them has to back up and let the other one pass. Simple, right? But what if neither driver is willing to budge? You know, maybe it's pride. Maybe it's just pure stubbornness. The result? A complete standstill. They're both stuck, waiting for the other car to do something. An event that is just never going to happen. That right there is a perfect real-world deadlock. Okay, so we've got the analogy. Now let's translate that stubborn standoff from the road into the language of computers, and formally define what a deadlock really is. In the world of computer science, a deadlock is basically when two or more programs or processes are completely frozen. Why? Because each one is waiting for a resource that another process in the group is holding on to. And since they're all waiting, nobody can make a move. It's the ultimate digital standoff. Alright, so now let's swap out our cars for computer processes, and that narrow road for digital resources, and let's see exactly how this whole thing plays out inside a machine. So, instead of cars, let's say we have two processes. We'll call them P1 and P2. And instead of the road, they each need access to two resources, R1 and R2. Now here's the critical part. P1 has a lock on resource R1, but it can't finish its job until it gets R2. But at the exact same time, P2 is holding R2, but it's waiting for R1. You can probably see the problem already. It's this perfectly inescapable logic loop. P1 is completely stopped because it's waiting for P2 to let go of R2. But P2 is stopped because it's waiting for P1 to let go of R1. Neither one can proceed, and neither is willing to give up the resource it already has. They are indefinitely and completely blocked. Now here's the thing. A deadlock isn't just a random accident. It's actually the result of four very specific conditions, all happening at the exact same time. Think of it like a recipe for disaster. You need all four of these ingredients in the mix to create total system gridlock, and these are the four conditions: mutual exclusion, no preemption, hold and wait, and circular wait. What's really cool is that if you can find a way to prevent even one of these from happening, the deadlock can't form. So let's quickly break down what each one actually means. First up is mutual exclusion. This one's pretty simple. It just means the resource can't be shared. Only one process can use it at a time. The classic example is a printer. You can't have two different documents printing on the same piece of paper at the same time, right? One process gets exclusive control. Second, we have no preemption. This means that resource can't be forcibly taken away from a process. The operating system can't just step in and say, hey, I need that now, give it back. The process has to release it on its own terms, usually when it's finished with its task. No one can force it to let go. Our third ingredient is hold and wait. This is where a process starts to get a little bit greedy. It's already holding on to at least one resource, say R1, but it's also waiting around for another one that's busy, like R2, so it's holding something and waiting for something else. And finally, the ingredient that locks everything into place, circular wait. This is where you get a chain of dependency. P1 is waiting for something from P2, which is waiting for something from P3, and this can go on until the last process in the chain is waiting for a resource held by, you guessed it, P1. It creates this perfect, unbreakable circle of waiting. So let's actually see how that final ingredient, the circular wait, creates this vicious cycle. We're going to visualize how a deadlock actually forms, step by step. Okay, so here's where we start. Process P1 has successfully grabbed resource R1. It has what it needs to begin its work, but not enough to finish it. Next, P1 makes a request for resource R2. It is now officially in that hold and wait state we talked about. It's holding R1 while waiting for R2, and here's the critical twist. There's another process, P2, and it's already holding R2. Then to complete the trap, P2 makes a request for R1, which of course is held by P1. The circle is now complete, and there you have it. P1 is waiting for P2, and P2 is waiting for P1. This closed loop is the circular wait, made visible. With all four conditions now met, these processes are officially in a deadlock. They will wait forever, and that right there is the crucial takeaway. All four of these conditions, mutual exclusion, no preemption, hold and wait, and circular wait, they must all be present for a deadlock to happen. This also means, if you can break the chain, if you can eliminate just one of these ingredients, you can prevent the deadlock from ever happening in the first place. So we know the recipe for gridlock. And that leads to the most important question of all. How do we break it? How are our operating systems designed to actually prevent this vicious cycle from ever starting? Well, figuring that out is the key to keeping our entire digital world running smoothly.